Okay, guys, welcome back. Discrete optimization. But still the knapsack problem, but today we're going to talk about modeling. Okay, so whatever I'm going to say today is going to seem very, very simple, but there are some deep truth and deep knowledge in what I'm going to talk about. But they will seem to be completely natural, but we'll come back to them later on, and you'll see why some of the things that I'm going to say today are actually important. Okay, so the first thing we're going to do is talk about how to formalize an optimization task as a mathematical model. This is the key. Okay, so this is the key for actually solving these problems. You have to be able to model them mathematically. Why? Let me give you an example. You talk with industry, you talk to people, they start describing your problem, and you think you understand it, okay? And then you come back with a beautiful solution and tell you, you can't do this. That's the constraints. But they didn't express it the right way, or they forgot to tell you. And essentially, you come up with this beautiful algorithm that really don't apply in practice. So what you have to do first is always find a description of the problems that everybody can agree upon. Okay, this is the first step. What is it that we are trying to solve? And that's what I'm going to talk about today. Okay, so let's do that for the knapsack, which is very simple. But that's going to give you an idea on how we do that for very complex problems. So we start with a set of items, capital I. That's all the items that we can actually put in the knapsack. And then for every one of these items, we will have two pieces of information, okay? That's what we have seen in the greedy algorithm so far, right? The weight of the item, okay? And the weight of the item and the value of the item. That's the two things that we know for the items. And then the only piece of information that you need is also the capacity of your knapsack. This is the input of your problem. That's what you need to actually start formalizing it. And now the problem is really finding a subset of these items, okay, which has maximum value. You want to maximize the value of the items that you are picking up, but you don't want the weight of the items that you are picking up to exceed the capacity of the knapsack, okay? This is still informal, and we're going to start formalizing this in the next couple of slides. But this is the start of formalizing the problem, okay? We know the input, okay? So how do we model this? The first thing you have to do every time you are trying to model an optimization problem is to find out what the decision variables are. And you're going to say, but what is this thing? Essentially, this is something that's going to capture the real decisions you are interested in, okay? In practice, for instance, in this particular case, for a particular item, what do you want to know? You want to know if you select that item or if you don't select it, if you put it in the knapsack or if you don't put it in the knapsack. That's what you want to decide, and that's the decision variables will correspond to that. Okay? So once you have these decision variables, you can start doing things with them. And one of the really important things that you have to do is basically model the problem constraints. And these problem constraints are going to tell you what you can do and what you cannot do. What is a feasible solution? A solution that people will tell you, yes, that's a solution, not something, no, you forgot something. It's basically capturing what you can do, what is a feasible solution. Okay? It's basically defining the set of things that people will accept as a solution. And then the last thing, obviously, is you have to define the objective function. What are you trying to maximize or minimize? And in this particular case, in the knapsack, it's going to be maximizing the value of your items. Okay? The objective functions is defining the quality of your solution. The constraints are defining what is a solution, and the decision variables are telling you what to decide, what you will decide upon. Okay? And so essentially, the result of these three things together is an optimization model. It doesn't tell you how to solve the problems. It tells you what the problem is. Okay? Now, a very important point here is that there are many, many ways of actually modeling a particular optimization problems. And this is part of the beauty. Okay? So in a sense, I'm basically telling you, we specify what we want to solve, but implicitly you are already making some choices, and it can restrict how you will solve the problem. So you have to be very careful when you do this. There may be many formulations, they may be translated from one to the other, but essentially they will capture the same problem in a different fashion, and they may influence the technique that you will use. So you have to keep an open mind when you model the problem, okay? So we'll come back to that many times, present different models of different problems for practical application. Now, in the knapsack problems, the decision variables, here are the decision variables. For every one of the items, you will have a variable xi. For item I, variable xi will denote whether you select the item or not, whether you put the item inside the knapsack or not. Okay? So xi will be equal to 1 if you select the item. It will be equal to 0 otherwise. Okay? So the goal of the optimization model will be to find the values of all these decision variables, whether you assign a 1 or a 0 to every one of them. That's going to be the goal. But these decision variables, when you see the value of them, you know what to do. Okay, every decision variable which is a 1, you know that you want to put them in the knapsack. The ones which are 0, you don't. Okay, so the problem constraints have to be expressed now in terms of these decision variables, and this is the only feasibility constraints that you have in this particular problem. What does it say? It basically makes sure that the item that you select, they will have an xi equal to 1, don't exceed the capacity of the knapsack. So basically what you do is you sum this product, okay, which has a constant which is the weight of the variables, and then whether you select the variable or not, and that summation here has to be smaller than the capacity of the knapsack. And when you don't select the item, this product is not going to contribute anything. When you select it, it will contribute the weight. So essentially this makes sure that you never exceed the capacity of the knapsack with the item that you select. Okay? Now, essentially, this constraint defines all the feasibility constraints. It basically makes sure that the item that you selected will not exceed the capacity of the knapsack. And then the last thing you have to do is express the objective function, and we use a similar expression. We multiply every one of these decision variables by the value of the item, the corresponding item. We sum them, and we have the full value of the knapsack. Okay? At this point, we have the decision variables, the feasibility constraints, the objective function. We have a complete model. This is the complete model of the knapsack. You see the value here that you're trying to maximize, and you see the capacity constraints over here, and then you know that every one of the decision variables had to take a value 0, 1. You take the item or you don't. Okay? And so this constitutes an optimization model. Everything here is formalizing what you want to do. You know exactly what's going to be a solution, and you also know the value of every one of these solutions. What remains to be done is what? Is finding the value for these decision variables. Now, you can look at these problems and you can start, well, but how many solutions are there? And in this particular case, what you can do is enumerate all the possible configuration for the values of the decision variables. Okay? So you can decide, for instance, that you select no item. That's not going to give you very much value, but this is one of the things that you can consider. Or some configuration where you select one item, or a combination with 2 items, 3 items, and so on. Okay? This is essentially your search space. When you look at the decision variables, the value that you can take, the Cartesian product of these guys are going to give you all the configurations that you have to consider. Okay? Not all of them are going to be feasible. Some of them are going to violate the capacity constraints. And that's going to be the feasible part of your search space. Okay? So this is going to give you the search space. This is the feasibility region in a sense. Okay? And how many are there? Well, essentially in this particular case, the number of configuration, if you ignore the ones that are violating the capacity constraints, is going to be 2 to the number of items. And that's a huge number if there is a large number of items. Okay? So let me give you an idea on how many and how fast this value is increasing. Assume that it takes 1 millisecond to test a configuration, to test if a configuration is feasible. And we try to enumerate all of them, test, and then we want to select the best one. We just, apply a brute force algorithm to do this. If it takes 1 millisecond to test any configuration, and you have 50 items, okay, it will take that number of centuries, more than wow, that's a huge number. It's more like 1 billion centuries to actually solve this, right? So this is huge, okay? So you can't solve the problem this way. And what this class is about is exploring this configuration in a smarter way, okay? And still finding an optimal solution, okay? Or in a sense, finding a very high quality solution that you can say is very, very close to the optimal solution. Okay, so next time we're going to start looking at how you can actually do that, how you can find optimal solution to the knapsack problems in reasonable time. Okay, see you next time. Thank you.